Thanks. I'm excited to be here. This is my first time to Kingfisher, so that was kind of cool. I got a lot of PowerPoint slides set up that I can go through, but feel free to stop me and ask questions anytime, and we'll talk about whatever interests you, and we can just start with what I have. Let me tell you a little bit about myself. I went to a small college in Los Angeles. I grew up mostly in California, though I was born in Texas, a place called Biola University. I got my PhD at UCLA. PhDs take a long time after college. Once you graduate from college, to get a PhD takes about 6 more years. So that means when you graduate from high school, you're about half done your education if you want to, go on to do something like this. Just something to think about, right? I'm now at OU. I've been there since for a long time. I'm an old guy, I think 18 years or something. Who keeps track? And I do my research at 2 places. One is a laboratory outside of Chicago called Fermilab. There's a picture of that. But mostly I'm doing my research these days at a place called CERN outside Geneva, Switzerland. And that's what we'll mostly talk about today. So as Mrs. Ice said, we ask basically 3 questions. And my way to phrase those questions is very similar to hers. What's the universe made of? What forces hold the stuff of the universe together? Or in other words, how does it all work? And what can we know about the beginning of the universe? And the kind of physics we do, the things we study, answer these kinds of questions. Now, I'll tell you what's cool about my job, is when you go to school every day, your teachers tell you things that people already know. Somebody else has already learned it, and now you have to learn it. When you're doing research, you're trying to find answers to questions that nobody knows the answer to. And so nobody knows what the right answer is. And it actually makes it really fun to try to pursue these kinds of questions. So how do you do this? How do you decide what the universe is made of? I mean, you can't see the smallest particles of matter. Has anybody seen a proton before? 1 proton or 1 electron? And so how do you determine, what the universe is made of? The first experiment to really do that was done in 1911 by a British guy named Ernest Rutherford. And here's what he did. At that time, have you guys ever heard this experiment? Some of you probably have in science class, yeah? Yeah, she's taught it, whether they've heard about it or not, right? That's 2 separate things. What the teacher says and what the student learns are always 2 separate things. But anyway, at that idea, in 1911, people thought there were atoms, but nobody really knew what an atom looked like. And one idea was that an atom was just like a bunch of pudding, kind of a mush of stuff together. And another idea, I'll go to this one, was that the atom was like plum pudding. And that was an idea that, the atom was like a pudding with kind of these soft plums in them. And the soft plums were negative or positive charge or something. So how do you determine whether the atom is more like pudding or more like plum pudding? Because you can't really see one atom. So the idea was you would shoot something through the atom. And if the atom was like pudding, whatever you shot through it would just go straight through, because pudding doesn't, stop things. But if the atom was like plum pudding, every once in a while, what you shot through it would be would hit one of these plums and bounce off a little bit. And so by seeing whether the things you shot through go straight through or whether they bounce off, you can kind of get an idea of what the atom is made of, even though you can't see an atom. So what Rutherford did was he took a really thin piece of gold, so thin that it only was a few atoms thick, and he shot particles at it called alpha particles, which are natural radioactivity. And what he saw was remarkable. Instead of going straight through or bouncing a little bit, every once in a while, the particles bounce straight back. And Rutherford wrote in his notebook that this was like shooting a cannonball at a piece of tissue paper and having the cannonball bounce back. Nobody expected this. And so Rutherford thought, well, how could you ever shoot this cannonball through this piece of tissue paper, well, really shoot alpha particles through gold foil, and ever have it bounce back? And so he came up with an idea. If all of the mass of the atom was concentrated at a very tiny point in the center of the atom, then when this particle hit that tiny point, it would bounce back. It's like, taking, all the mass of the atom and making a huge brick wall, but only right at the center. And it was that idea that led him to our idea of the atom now, that center part is called the nucleus. And the nucleus is where most of the mass of the atom, is there. And this is how we discovered the nucleus. No one has ever seen a nucleus with their eyes, but we can do experiments to know that most of the mass of the atom is at a very tiny point right at the center. And so everything we do is develop models. We look at nature and we try to say what picture of nature corresponds to what our experiments tell us. If our experiments say things bounce back, the picture of nature that corresponds to that is that there's a nucleus. And so we develop models of the atom like planetary models or orbital models. These orbital models you'll study in chemistry based on our experiments. Now, anybody recognize this here?
That's us.
That's us, right? There's your school. Okay, so we're sitting, I don't know where we are, somewhere there. So how big is the nucleus inside the atom? Well, if you were to take a baseball and just stick it right in the middle of school, that would be the nucleus of the atom. That's where all the mass is. How big do you think the atom would be if the nucleus was the size of a baseball? Pretty big. It would be about this big. Okay? So all of the mass of the atom would be a little baseball right in the middle of the school, and all of this area, you know, halfway to McDonald's or whatever, is the size of the atom. So the atom is mostly just empty space. And the nucleus with all the mass is a little tiny bit in the middle. And that's what Rutherford was hitting. And so we discovered this not by actually seeing the atom, but by colliding particles together, colliding alpha particles on gold foil, and looking and seeing what we saw. All right. Any questions so far? Does that make sense? How many of you have actually heard of Rutherford experiment? I want to know. Well, I can't. More than that. All right, good. You better have, right. All right, so what do we do now? That was 1911, so that was 100 years ago. We still smash particles together. The same way Rutherford shot alpha particles into gold, the way we still probe what matter is made of is by shooting particles together and seeing what comes out. And the major places it's done in the world now is something called the Large Hadron Collider. I'll explain what that means in a little while. I'll just read this. It's the most expensive, complex, and largest machine ever built by humans. It's located on the French-Swiss border in a tunnel about 300 feet underground, and it accelerates trillions of protons to nearly the speed of light in an attempt to understand more about the origin of the universe and the structure. So again, the idea is instead of just having a piece of gold foil and shooting a single particle at it, I'm going to get two sets of particles going extremely fast, almost the speed of light, in different directions, and then I'm going to smash them together. And we'll talk about why we do it that way in a little while. But so here's what it looks like. About 300 feet underground is a tunnel, and a few places in the tunnel where this says Atlas, Alice, LHC, CMS, we build huge detectors to see what happens when the particles collide. And this is where I do my research. So if you come to the University of Oklahoma and you want to do research in particle physics as a PhD after you get a bachelor's degree, you would work with me or somebody, you know, and eventually you would spend a year or two here in France and Switzerland so that you could actually work on this experiment. So we have graduate students who are from Oklahoma who now live in Switzerland or France, and we talk to them every day by video and things like that because they're working on these experiments. This thing is huge. Here's what it looks like in a picture. The tunnel's underground, so you really don't see anything. The diameter of the tunnel is 5.5 miles around, so it goes under farms and under cities. Here's the Geneva airport. Here's Lake Geneva. And nobody even knows it's there. It's just deep underground. And there's a few places underground where we have these detectors. So if it's 5.5 miles in diameter, it's about 17 miles in circumference. And here's what it looks like 300 feet below ground. We're inside a tunnel, and the accelerator is actually inside this big machine here. These big blue things are magnets. We use magnets to steer the protons. There are 1,232 what we call steering magnets, and they're cooled to minus 456 degrees Fahrenheit. So really, really cold. And that's so the magnets work right. Let's see. What else? It's about $10 billion, so it's not cheap, but it actually is cheap for what you get. Only $10 billion